Section 10.5, chemical equilibrium in the electrolyte solution. We'll do some calculations in this section. So there's another way to define the activity. So this activity is the activity coefficient times C over C naught. C is the molarity, C naught is just 1 molar. So this is often used as well. Now let's look at the solubility product of a ionic compound. Let me give you an example here. Magnesium fluoride, the KSP, the solubility product, is simply the activity of magnesium 2 plus times the activity of fluorine minus to the power of 2. You saw similar equations before in general chemistry, but in general chemistry I think you did not see A, you saw C. Alright, C, the molarity. But now let's be more accurate. We're going to use the activity. We'll take the lowering of the activity of these ions in water into account. The activity coefficients of ions are always less than 1. Now let me give you the solubility equilibrium constant for magnesium fluoride. It's this number. It's not very big. It's 6.4 times 10 to the power of negative 9. Pay attention here. There's no unit because over here the activity has no unit. It's gamma, which is unitless, times C over C naught. This C over C naught gets rid of the unit. Now let's look at the calculation. KSP is equal to the product of the activities, or this gamma to the power of 3 times the concentrations or just molarity of those ions, and how do we compute the actual concentrations, saturated concentrations of magnesium fluoride? Well, here it is. We need to compute this gamma plus minus, and then we plug it in, and then we get C, right? So it sounds simple, but it's more complicated. We're going to have to do some iterations. I'll show you why. First, this gamma plus minus, that's the geometric mean of the activity coefficient. To the power of 3 because we have 3 particles or 3 ions, 1 magnesium 2 plus and then 2 fluorine minus. That's why. Now how can we determine this gamma plus minus? See, we have this equation ready to use. You just need to know the ionic strength, right? How do you calculate the ionic strength? Well, it's very simple. You just need to know the concentration of the electrolyte, right? So how do you know the concentration of the electrolyte? Ideally in molar, but if it's in molar, I mean it's about the same. Okay, 1 molar is about the same as 1 molar in a aqueous solution, because 1 liter solvent usually contains 1 kilogram of water. Usually, if the solution is not too concentrated. But now let's get back to this I. You do need to know how much magnesium fluoride is dissolved in water before you can calculate I, and that's actually our goal. Our goal is to determine the concentration of magnesium fluoride. So it seems that we are stuck. But here's the iterative algorithm. We make an initial guess. Okay, we make an initial guess of either I or the concentration, whatever, and then we can calculate the other. If you make a guess of I, you can calculate concentration. If you calculate concentration, if you guess initial concentration, you can calculate I, and then you get to repeat these steps every time. You get a different number. So in the end, the last 2 steps spew out the same numbers, and then you say stop. We're done. We got the calculations converged. All right. So now let's look at the formula of this ionic strength again. This is molarity over 2 times the sum of the coefficient of the positive ions, the charge of the positive ions to the power of 2, and then over here the coefficient for the anions and then the charge of anions to the power of 2. Alright, so we'll have to kind of just make some initial guess. This time we can just guess the coefficient is just 1. So basically we're saying, well, why don't we take a guess of the ionic strength? We say it's 0 for convenience. Of course it's not 0, but we're just like, well, it's very close to 0. So the gamma activity coefficient is just 1. And then we can easily get the concentration of magnesium fluoride because, look, this gamma plus minus is just 1. Isn't that simple? So KSP is just 4 times the concentration of this magnesium fluoride to the power of 3, y to the power of 3. Okay, the thing is, if you dissolve 1 magnesium fluoride in water, you will get 1 magnesium 2 plus and 2 fluoride minus. And somehow the concentration of this fluorine 2 is twice the concentration of magnesium fluoride. And it has to be squared, that's why you have a 4 here. So when that's the case, you just solve this equation, you have KSP, and then you solve this C, that's easy enough to do. C is 0.00117 molar here. Alright, and then this is low concentration, so we say 1 molar is roughly 1 mole. So we get the molarity as well, roughly this. We're not done, because we assumed the activity coefficient is 1. It's not 1. Because we have ions, this much ions in water. So this time we recalculate this I. This I is not 0. So we plug in the numbers. This is the coefficient of magnesium, the charge of magnesium, the coefficient of fluoride, the charge of fluoride. Now we have this ionic strength. It's 0.003. It's a small number, but still it makes a difference. We plug in this square root of I here, and then the charge of magnesium and fluoride. We got the logarithm of the activity coefficient, and then activity coefficient is 0.87. This time we plug in this 0.87 here instead of 1. This is more realistic. And we compute the concentration again. This is 0.00134 molar. Okay, this is bigger than the previous number. Look, this number, this molo, this 117 molar, 134 molar, 134 molar, 117 molar. We get a higher concentration only because we took the ionic strength into account. That means the activity of magnesium and fluoride are lowered. That means it's possible to dissolve more magnesium ions and fluoride ions due to their stability in water. So we recalculate this I using the new number here. So we get a new I, and then we get a new gamma, and now we get a new concentration in molar, and then we convert it to mole actually by just estimating this. They're about the same. Okay, and we're not done yet because this number, this concentration 136, is different from 134. So maybe just one more iteration because we are getting really close. Now plug in this molarity into the equation for I. Again, 1/2 of this molarity times the sum of the coefficient times the charge squared. Coefficient times the charge squared. If you have multiple electrolytes in water, again, you just sum up all the ions. And then we get a new I, we get a new gamma, we get a new gamma here, and we get a new concentration. This concentration is the same as this concentration in the previous step. And then, well, there's no point to keep doing this iteration. We say the calculation has reached convergence. Alright, so this is a little complicated, but this algorithm is very important. It's very useful in physical chemistry and many other sciences. Finally, let me explain, two different phenomena. They are called sort in, sort out. So if you are trying to dissolve something, if you put, additional salt in water, sometimes it increases the solubility, sometimes it decreases the solubility. So they are called sort in, sort out. Sort in. You learned what sort in is. If you add actually sodium chloride into magnesium fluoride, that will increase the ionic strength, and that will decrease the activity coefficient. That will stabilize magnesium and fluoride. That will enhance the solubility of magnesium fluoride. Qualitatively, we don't have to kind of use any equations. We'll just say, well, fluoride will be surrounded not only by water, but also by sodium plus ions. There's going to be additional attraction from sodium plus. How about magnesium? Magnesium 2 plus will be surrounded not only by water molecules, but I'm pretty sure, some chlorine minus will be getting close to magnesium 2 plus. So that way you enhance the stability of magnesium 2 plus and fluorine minus in water, and then you increase the solubility of magnesium fluoride. Okay, make sure that you use different ions, sodium chloride, sodium nitrate, all okay. If you use sodium fluoride, okay, bad. If you add sodium fluoride, you arbitrarily increases the concentration of this fluoride, and then that will reduce the solubility of magnesium, magnesium. Okay, I'm sorry, Mg2 plus. And then you have a very low concentration of this magnesium fluoride. All right, magnesium. So this is salt in. So in the end, salt in is very simple. You just add some other ions to increase the attraction. Okay, to increase the attraction, to dissolve more. Okay, to dissolve more. Again, if you want to dissolve silver chloride, you can add a sodium nitrate. You add a sodium nitrate to increase the solubility of silver chloride or silver bromide, because again, silver plus will be attracted by nitrate, and the chlorine minus will be attracted by sodium plus. By adding sodium nitrate, you increases the stability. You decreases the activity coefficient for silver chloride. Now sort out. Well, that's a completely different mechanism. If you're trying to dissolve protein, okay, it's hard enough because you need to have a lot of water molecules to interact with the hydrophilic part of the protein to dissolve it. And then if you add a very large amount of salt, like sodium chloride, these sodium plus and negative chlorine minus ions will attract the water molecules. And then there will be fewer water molecules available to interact with the hydrophilic parts of the protein. And the protein, losing these hydrogen bonds, they start to coagulate. So that means they're trying to somehow lower its energy, compensate this hydrogen bonding by having the hydrophobic part interacting with the hydrophobic part. Well, that's mostly dispersion. So adding salt reduces the solubility of protein in water.